PID controller. A PID controller is an instrument used to regulate temperature, flow, pressure, velocity, and other process variables. The PID control works much the same way as the cruise control on a car, where external influences such as hills would decrease speed. The PID algorithm restores from current speed to the set point speed by controlling the power output of the vehicle's engine. The PID stands for Proportional Integral Derivative Control. As its name implies, a PID controller combines a proportional control with addition, integral, and derivative adjustment, which help the unit automatically compensate for changes in the system. So basically, the PID controller job is to measure process condition and calculate feedback, and adjust output to force the process level to match a set point. So for another example is a thermostat. It forces the heating and cooling unit to turn on or off based on a set temperature. And that's all. Thank you.
PD controller, proportional derivative, device output signal. There are two types: proportional input signal, derivative input signal, increase damping, reduction in peak overshoot. TF means transfer function equals GC S KT plus KDS. Proportional derivative controller produce an output which is a combination of the outputs of proportional and derivative control. The proportional derivative control is used to improve stability of control system without affecting the steady state error. Thank you. Next is all about P controller and PD controller. P controller, proportional controller, device output signal, proportional input signal. Improves SSE stability. Decrease sensitivity parameter. Disadvantage: constant SSE means steady state error. TF GCS equals KP. TF means transfer function. Proportional control engineering and process control is a type of linear feedback control system in which correction is applied to the controlled variable which is proportional to the difference between the desired value. Thank you.
So good day everyone, we have here the black diagram of temperature control system of heat exchanger. So we have here the controller, bulb, heat exchanger, actual temperature, our desired temperature, and of course our sensor. So let's start the sensor. So this sensor senses the actual temperature and send it back to our controller. So this is our actual temperature, and the sensor senses the actual temperature and send it back to the controller. that compares with actual temperature to our desired temperature or our set point, temperature set point. So the controller automatically close and open the bulb, this bulb, to allow or to prevent the flow of steam to bring back the temperature of the heat exchanger to our temperature set point.
My assessment is all about design a simple process control system for a heat exchanger using a P controller and the final control valve. A proportional controller decreases the average power supply to the heater as the temperature approaches set point. This has the effect of slowing down the heater so that it will not overshoot the set point, but will approach the set point and maintain a stable temperature. This proportioning action can be accomplished by turning the output on and off to short time intervals. This time proportioning varies to the ratio of on time to off time to control the temperature. The proportioning action occurs within the proportional band or at the set point temperature. Outside this band, the controller functions as on-off unit with the output either fully or fully off. However, within a band, the output is turned on and off in the ratio of the measurement difference from the set point. At the set point, the output on-off ratio is 1:1. That is, the on-time and off-time are equal. If the temperature is further from the set point, the on-off varies in the proportional to the temperature difference. A temperature control valve is just like any other control valve. The only difference is that the control valve helps to maintain the temperature of a desired process at a specific level. It is often abbreviated as TCV in most process drawing and PIDs. In the heat exchanger scheme of temperature control, mixing does not take place, but what takes place is energy transfer between the cold and hot fluid. The hot fluid passes through the shell of the exchanger while the cold fluid passes through the tube. The hot process fluid transfers energy to the cold process fluid, thereby increasing its temperature. However, the elevated temperature of the cold fluid is controlled by the controller, TC. As shown above, the same temperature control philosophy applies here with the temperature transmitter, TT, sensing the temperature of the cold fluid and transmitting it to the temperature controller, TC. If the temperature of the cold fluid is above set point, the controller initiates a control action by sending a signal to temperature control valve.